Light interference helps us to explain why some animals have eye shine. If you shine a light into some animals' eyes, they will always glow the same color. The reason for this is a structure that these animals have called the tapetum lucidum. It's a thin membrane at the back of the eye that reflects light back through the retina. So with these animals behind the retina, where the light collecting cells are, there is a very thin membrane that reflects the light back through the retina. This means that the retina has two chances to catch the light, and this makes these animals' night vision a whole lot better. They can see better in dim conditions because the light has two chances to get caught. Now this does reduce the acuity of their vision, and so the images that they see aren't quite as sharp as human vision when we don't have this structure. So there is a bit of a trade-off. But one question we could ask is, how is it that this membrane always reflects the same color? So if you shine a light into a cat's eyes, you're not going to get a different color reflection. Even white light will always give you the same color. And if the membrane acted like a mirror, it would reflect all colors equally. But for some reason, a specific wavelength is picked out. And so we need to understand why is that? Why is a thin membrane good at reflecting just one color? So this has to do with the fact that if you have a thin membrane that has an index of refraction different from what is around it, then light undergoes shifts upon reflection from that membrane. And it undergoes different shifts off the different surfaces of the membrane. So the important principle here is that light is shifted by half a wavelength if it reflects off of a higher index of refraction material. So if we look at this thin membrane or thin film with different indices of refraction, so there's this thin membrane here, it has a higher index of refraction than its surroundings. So you have low, and then you have a higher index of refraction, and then another low index of refraction. Light will reflect off of both the top and bottom of this membrane or film. When light reflects off the top, it's reflecting off a higher index of refraction material. So originally it's traveling through N1, which is a low index of refraction material, and then it reflects off the higher index of refraction material, N2. So light travels slower through a higher index of refraction material, and so this reflected wave is inverted. The same thing happens with waves on a string. So this is this case here. So first we're going through a fast material, a light string, and then we encounter a boundary with a heavier string. And you can see that the reflected wave is inverted. That's what's going to happen. So if you send a wave pulse down and it encounters a string where the wave travels more slowly, the reflected wave will be inverted. And the same thing happens with light waves. If you encounter a boundary between low and then a higher index of refraction material, the reflected wave off the high index of refraction material is inverted. It's inverted so that the wave is doing the opposite thing. Now the reflection that happens off of the bottom of this material is reflecting off a lower index of refraction material. So that's like going from a low speed string that's heavy to a high speed string. The reflection that happens at that boundary is not inverted. It's still right side up. And the same thing happens when you reflect off a low index of refraction material. If you're already traveling through a higher one, that reflection is not inverted. So we get these two different waves coming back off of the membrane or the film. One that's been inverted and the other one that has not been inverted by its reflection at the bottom. Now this wave also travels through an extra amount of distance, and so that if that extra distance is such that the reflected wave off the bottom matches the reflected wave off the top, then you'll get constructive interference of a specific wavelength. And if it is 180 degrees offset, then you will get destructive interference for that wavelength. So just as a reminder of how phase shifts are related to wavelengths, one full wavelength is 360 degrees or 2 pi radians. So if we say we have a phase offset of a full wavelength, then that's equivalent to 360 degrees. If you have a relative phase shift of 180 degrees between two different waves, that means you've shifted by half a wavelength and you will get destructive interference. If you have a phase shift of a whole number of wavelengths, so say one complete wavelength as is shown here, then you will get constructive interference. So a whole number of 360 degree phase shifts or a whole number of wavelengths gives you constructive interference. So let's next consider a couple of different scenarios where we have a thin film that's surrounded by a different material. First, let's consider the case where light is going from air to soap to air. So here we have a low to high to low index of refraction set of boundaries. So the light that reflects off the top is reflecting off a high index of refraction material. So because of that, it will pick up a 180 or half wavelength phase shift. So the reflection shift for ray 1 that reflects off the top of the film is half a wavelength. The light that reflects off the bottom of the film is reflecting off a low index of refraction material, and so this low index of refraction material does not give us a phase shift. So its reflection phase shift is 0. However, this second ray of light travels an extra distance when compared to ray 1. It has to travel through the thickness of the film and then back up again. So it picks up a distance shift of two times the thickness of the film. So if this particular wavelength of light is to undergo constructive interference, so we get a bright region in that color on the top of the soap film, then that extra distance has to make up for the phase shift of half a wavelength that we got because of the reflections. So that means that 2t, 2 times the thickness of the film, that's the extra distance that ray 2 traveled, has to be equal to a half wavelength in the film, and then you can have an additional whole wavelength or whole sets of wavelengths. But there has to be that extra phase shift of half a wavelength. You'll notice there's also this lambda divided by n. We've divided the wavelength by n, the index of refraction of the film. In this case, that would be the soap. And this lambda over n occurs because the wavelength in the film changes. We know that the wavelength of light changes as you're going through different indices of refraction materials, and this is the wavelength in the film. So basically what we're saying is that this extra distance that this wave travels has to be equal to a half wavelength shift to make up for the half wavelength difference upon reflection, and that wavelength in the film has changed. So this is the condition that we have to meet in order to get constructive or bright reflection off of the top surface of this soap film. On the other hand, if that extra distance that ray 2 travels is equal to a whole number of wavelengths in the film, then we get constructive or destructive interference, and that color will not be reflected brightly. It will be actually transmitted through the soap film, and so you won't see that color appear brightly on the surface of the film. Now let's look at a different situation. So before we had a low to high to low index of refraction set of materials. What if we had air on oil on glass? Here we're going from low to high to even higher indices of refraction. Because of that, there is a phase shift for both reflections. You get a phase shift off the top surface because you're reflecting off a higher index of refraction material, the oil, and then you also get a phase shift for the reflection off of the bottom of the film because you're reflecting off of glass, which is even higher than oil. So both of these reflections give you a half wavelength phase shift, so they would naturally match up. Only this ray travels that extra distance of twice the thickness of the film. And so that extra distance needs to be a whole number of wavelengths, since you already have matching because of the reflections. So it's a whole number of wavelengths within the film. And so this is the condition for getting a bright spot of that color on the surface of the film. On the other hand, if you have that extra distance traveled by ray 2 equal to some half number of wavelength shifts, so you get half plus maybe some additional whole number of shifts times the wavelength in the film, then that's the condition for getting destructive interference. So that type of, or that color of light will not appear on the surface of the film. Let's look at a couple of example problems that involve constructive and destructive interference off of these thin films. So in this first example, we want to know what wavelength monochromatic source, so single wavelength, in the visible region can be used to constructively reflect off of a soap film if the film is 240 nanometers thick and resting on water. So you can see here is a picture of that kind of interference pattern that you get on top of a soap film. So the reason why there are different colors here is because typically a thin film will vary its thickness in different regions. And so the different regions will each reflect strongly a different color. So, but we're looking at a particular region where the film is 240 nanometers thick. So let's draw a picture of the reflections and consider what kind of indices of refraction that we're dealing with. So in this case, we have our thin film, and our thin film is made of soap. So above that thin film of soap, we have air. So the index of refraction is equal to 1. Then the soap itself has an index of refraction of 1.46, and it's sitting on top of water, and water has an index of refraction of 1.33. So if we think about the kinds of reflection we're getting, we have a reflection off the top surface of this film of soap, and this reflection off the top surface is going to have a phase shift of half a wavelength because we are reflecting off a higher index of refraction material. So this phase shift here is going to be 180 degrees or half a wavelength. Now the phase shift that happens upon reflection off the bottom of this film is actually going to be 0. We're in a high index of refraction material, we're reflecting off a low index of refraction material, lower than the 1.46. So this phase shift is going to be 0. So because we have this half wavelength phase shift because of the reflection off the top of the film, the journey through the film has to make up for that half wavelength offset. So the condition that we're looking for is that 2nt, so here I just moved the n to the other side, is going to be equal to a half wavelength shift, m plus a half, times lambda. So before we had lambda over n, and I just multiplied both sides by n. But basically what this is saying is that the extra journey through the film for the second ray has to make up for the half wavelength shift. So we need m plus a half times lambda in order to figure out where we get constructive interference. So we want constructive interference in this case. Now we want to know what wavelength, so we need to solve for lambda. So lambda is going to be equal to 2nt divided by m plus 1/2. Now we know what n is. N is always the index of refraction of the film, so that would be 1.46. We know the thickness of the film is 240 nanometers, and we need to know what m is. The problem doesn't say what m is. M is an integer, but we don't know what m is, and so basically what we need to do is try different values of m, and then see what gives us lambda in the visible region, so between 390 and 710 nanometers. So first off, I'll try setting m equal to 0 and see what that gives us. So if we do that, lambda is going to be equal to 2 times the index of refraction of the film, which is 1.46, times the thickness of the film, which is 240 nanometers. And you notice I'm keeping this in nanometers. I can get away with that because everything else here doesn't have units. And then we divide by m plus a half, and I've set m equal to 0, so this would just be 1/2 or 0.5. So if I do that calculation, I find that I get a lambda of 1,402 nanometers. So that's actually outside the visible range. It's in the infrared, actually. So let's next try m is equal to 1. It's outside the visible range, but not hugely so. So maybe m equals 1 will give me a wavelength in the visible range. So here lambda is equal to 1.46. The thickness is 240 nanometers. And then I have m is 1, so 1 plus a half is 1.5. And that's going to give me a wavelength of 467 nanometers. And that is within the visible region. So that would be the result that I want. That is the color that I'm going to see at that particular spot in the soap film that has a thickness of 240 nanometers. So next, let's consider this problem. So this figure, and that's the figure here, shows a typical tapedum lucidum structure for a fish. The reflection comes from the interfaces between two layers of nearly transparent cells, whose index of refraction is essentially that of water, and a stack of guanine crystals sandwiched between. What is the smallest thickness of the crystal layer that would lead to constructive interference, or eyeshine, for a light of wavelength 558 nanometers? So for this problem, we have a different film. The film is the guanine crystals. And so if we draw a picture of that situation, we have this layer of crystals which has an index of refraction of 1.83 according to the figure, and it's sandwiched between cells that have indices of refraction that are essentially that of water. So the n is 1.33 above and 1.33 below. So if we look at the phase shifts that we get, we have the reflection off the top surface of the crystals, and that reflection off the top surface, since it's reflecting off a higher index of refraction material, there's going to be a phase offset of 180 degrees, which is half a wavelength shift. Now, the reflection off the bottom of this layer of crystals is going to be equal to 0 because we are reflecting off a lower index of refraction material. So this phase shift is 0. So if we look at this situation, we once again want constructive interference because we're looking at the eye shine, what wavelength is reflected very brightly. And so we want constructive interference, so we need, with this second light ray, we need this extra trip through the crystals to give us a shift that is equivalent to half a wavelength shift that the first ray of light got through its reflection. So that means that we can write down for the condition for constructive interference that 2nt, the effective distance through the crystals, is going to be equal to m plus a half times lambda. Now this time we're looking for the thickness of the crystal layer. So we want to solve for t. So t is going to be equal to m plus 1/2 times lambda, and we divide that by 2n. So we know what the wavelength is that we want the eye shine for, And we know the index of refraction of the thin film, which in this case of the crystals, 1.83. But once again, what's m? What do we use for m? Well, the key phrase in this problem is that we want the smallest thickness. So for the smallest thickness, for the smallest thickness, we want to have t be as small as possible, so we want the smallest possible value for m. So in this case, we would say that m is equal to 0. If we set m equal to 0, then we still have a film, but m is as small as we can make it. Now, if on the other hand we were looking at destructive interference, we would be looking at 2nt is equal to m lambda, and for this expression, the smallest thickness would be when m is equal to 1. That would be the smallest thickness condition, because if m is equal to 0 for this expression, then you don't have a film at all. The thickness would be 0, the film wouldn't exist. So if you have this expression, then the smallest thickness comes from m being equal to 1. But if you have this expression for your constructive interference, the smallest thickness possible is for m to be equal to 0, and in that case you still do have a film. So if we set m is equal to 0, then we have 1/2 times lambda over 2n. Or simplifying this further, that's the same thing as lambda over 4n. So if we put in some numbers, lambda, the wavelength of light, is 558 nanometers. And then we divide that by 4 times the index of refraction of the film, which is 1.83. So for that, we get a thickness of the crystal layer of about 76.2 nanometers. So that's the thickness of the layer at the back of the fish's eye. Let's next consider this question. Monochromatic light shines on a pair of identical glass microscope slides that form a very narrow wedge. The top surface of the upper slide and the bottom surface of the lower slide have special coatings on them so that they reflect no light. The inner two surfaces have non-zero reflectivities. So essentially, you have an air wedge between these two glass slides. What would a top view of the slides look like?